Okay, hello everyone. Like I said in class, I wanted to do a video for complex eigenvalues since we do have to move on. And yes, so I want to do that now. Now your book, which again, it's important to go over and look at how they, even if you don't understand everything, just kind of read it and skim this section. And so your book talks about it, and it gives you sort of the background theory and proofs, which you could definitely go over it to get an even better understanding. I'm just going to give you sort of the nuts and bolts that you'll need to proceed forward. But if you want to come and see me and we go over some of the proofs or whatever, that's fine. All right, so here we have this complex eigenvalue, and I would suggest you pause the video and write this stuff down, and then we'll come back over it, okay? And so we know this is back in 8.2, so I know we've started talking about non-homogeneous linear systems, but this is just homogeneous linear systems. And so we already know we go and find our eigenvalues, take the determinant of A minus lambda I. I save space there, so this is what you should get, and you end up with lambda squared minus 10. Lambda plus 29, and then using quadratic formula is not an easy factor, or it's not an easy form for us, so we use quadratic formula. Is actually complex, which we knew that from the heading. And so we have our eigenvalues 5 plus or minus 2i, okay? And so we can look here, and yes, so we have lambda 1 equals this, and then lambda 2 equals 5 minus 2i. And so here we see that I did the method that I showed you all about A minus lambda I and multiplying it by x1 and x2 and I should have said equals, you can put if you want, equals 0, 0. And then it goes here. Now, equation 1 is actually a multiple of equation 2. And so I will give you extra credit on the quiz to show why that is true. If you can show why equation 1 is a multiple of equation 2, so you have to show it algebraically. Show me what's that multiple that you're multiplying equation 1 by to get equation 2. Then you can get an extra point on the take-home quiz. Okay? So we have that. So using 1... and again, you can pause the video if you want to write this down. Y sub 1 equals, and we talked about in class, if they're multiples, we only need to focus on one equation, right? So I focused on the top equation, solve for y sub 1, and then if we let x sub 1 equals 1, then y sub 1 is 1 minus 2i. So here we have this eigenvector, which is sort of makes sense that if our eigenvalue is complex, then our eigenvector also will have an imaginary term in it as well. And so similarly for lambda 2, 5 minus 2i, the eigenvector is going to be 1, 1 plus 2i. Okay, so in general, this would be our solution here. Okay, and since lambda 1 is, here's a special note since we're dealing with complex numbers, lambda 1 is 5 plus 2i, we'll also give the conjugate, lambda 2, 5 minus 2i, we conclude that the eigenvectors will also be conjugates. Okay, so whenever you're dealing with a complex number, you already know, this is back actually from pre-calc, that when you have a complex solution, that its conjugate is also a solution to whatever equation you're working with. And so now we could take this a little further in terms of what we've been talking about and just say that if we have whatever our eigenvector is for that complex eigenvalue, the conjugate of that eigenvector will be it for its conjugate. Okay, and the notation that your book uses, and you may see, is if we have k1 e to lambda 1 t, okay, we know k1 is standing for what? Our eigenvector. Lambda 1 is our eigenvalue. The conjugate, so it's a bar to represent the conjugate of k1 and the conjugate of our eigenvector. Okay. Now, we would like to just, of course, stop right there, right, and be done. However, for most of our problems, we don't want to deal with imaginary terms. We don't necessarily know how to approach them. And in real world problems, imaginary numbers wouldn't make sense. So here's what, and again, if you want an explanation of how everything sort of came to be into this new general solution, then please see the book. They actually do a good job in showing in detail. You just have to go step by step to make sure you understand and play around with some algebra, but they actually do a nice job showing how they get this, how they derive this. But x equals C1, and notice that this is capital because we're adding two of our C1 and C2, the sort of smaller ones. We're putting that together to form our big C1. And then C2 is C1 minus C2i. Okay. And so now the general solution becomes, because again, we don't want to deal with imaginary numbers, C sub 1 times X sub 1. And X sub 1 is this expression here. And it looks like a lot, but it's really not when you break it down. And X sub 2 is this expression here. And so really, if you understand one, then the second one, you can finagle. You just have to remember the big difference is you switch. The big difference is you see these are switched and then you have an addition and subtraction there. But here's the thing. So don't get confused with the Greek letters versus the capital letters. This B sub 1 and B sub 2. And in linear algebra, you may remember, you don't have to do this, but to signify that you're talking about a vector, we usually put like a little arrow on top to represent a vector. So B1 and B2 are vectors. And in fact, you only need to look at one of your eigenvalues to get B1 and B2, because B1 is the real part of your eigenvector and B2 is the imaginary part of your eigenvector. Okay, alpha and beta are the same when we've dealt with any complex number, right? So that's from the here where alpha is our real part, right? And then beta is our imaginary part. So that's the same. All right. So from example 4, if we just look at lambda 1, or I don't know, was it lambda 1 or lambda 2, but whatever. It was lambda 1, 5 plus 2i. So 5 is our alpha, right? That's the real part. 2 is our beta. That's the imaginary part. And then what we do is once we have this eigenvector, we break it up and this will represent the real part. Okay, and the book uses RE for real, and then the imaginary part, the imaginary vector. So this is why you only need to find, when you have complex solutions, eigenvalues, you only need to find one eigenvector to solve your general solution, which is nice. Okay, so now putting everything together and substituting in, we have C sub 1 times the quantity. And again, remember, I'm getting this information. Let me make sure. I know it's a lot of writing going on, but this entire thing is representing our X sub 1. So it's B sub 1, which is the real part, right? So 1, 1, the vector 1, 1 times cosine of 2t minus the imaginary vector B sub 2, which is 0, negative 2 sine 2t e to the 5t, because that's our real part in the alpha plus beta I. And then C sub 2 is you flip the vectors, the eigenvectors. And so now it's 0, negative 2 cosine 2t, and then you flip the sign plus 1, 1 sine 2t e to the 5t. So this is what you'll be using if you have like an initial value problem that you have to, or in general, any application, which is where we're actually going to go to in chapter 10, is looking at graphs of these solutions. And so you would definitely need to use and know this method. Okay. So you'll probably get, I don't know if I'll give you any credit, maybe some partial credit, but for full credit, you need to know this method. Okay. And I'll probably state on an exam or something, no imaginary, only real terms. Okay. I hope that made sense. I also wanted to now go to 8.3 and look at the complex eigenvalue and sort of examples, similar, well, not similar, but now dealing with non-homogeneous. So again, we have, and I'm going to skip some parts because I want you to fill in the notes. Okay. So you can sort of pause the video and fill in the missing parts to make sure that my work is correct, because I can make mistakes. But for this, the first thing we need to do is solve the homogeneous. So remember, we talked about in class for a nonlinear system, remember, because this is our f of t, for a nonlinear system, the solution will be x sub c, which is our complementary solution, plus our particular solution. So similar to 4.4 and 4.6, we're just now looking at matrices and vectors. Okay, so the determinant of this, and again, double check my work, but it should be lambda squared equals 1. No, I think it should be plus 1. See, I'm messing up already. Should be lambda squared plus 1. Otherwise, it wouldn't be complex. Okay, and so, which tells us that lambda is plus or minus I. And so, remember, we only need to look at one of our lambdas. So this is 0 plus I, right? So in terms of thinking that's alpha's got to be 0, and then it's really a 1 there. So beta is 1, right? Because it's really 1 times I. We just don't write it there. Okay. Now we find our eigenvector. So for lambda equals I, you should get one of your eigenvectors. And again, I want you to double check this is 1 minus I and 1. So I want you to double check to make sure. And of course, this is assuming that you pick the right values. And yours could be different, right? Your eigenvector could be different depending upon what you let it be. What you let your x sub 1 and y sub 1 be. But see if you can get the same here. So again, I'm skipping that. Then we take out the real part and the imaginary part. So the real part, remember, is our b sub 1. And the imaginary would be b sub 2. Okay. And so that tells us that x sub c is c1. And you may have to refer back to what we just did, but it's the real vector cosine t, right? Because beta's 1, minus negative 1, 0 sine t. And this is e. Oh, it's no e, right? Because e to the 0 is just 1. So yes, so that goes away. No imaginary. I mean, no imaginary, no exponential. All right, and then plus c sub 2. And actually, let me make them. I guess I should make it a little more capital. It's sort of implied, but yeah. And this will be negative 1, 0. So now it's the imaginary part with cosine plus the real part with sine. All right, and again, since alpha 0, we don't have e to the 0 of t is just 0. Okay, so I want to bring this together. So what we have is c1 was cosine t plus sine t, cosine t. Okay, plus c2 sine t minus cosine t, sine t. And like I said in previous videos, I like to stop at the 15-minute mark, and I think it's going to take us longer than 3 minutes. Sorry, that's my phone. But I think it's going to take us longer than 3 minutes to do. So I'm going to stop this video and start a new video to finish this problem.